Welcome to the second vodcast in Topic 5 Electricity and Magnetism. We're going to look at the electric field section in a little bit more detail. Specifically, we're going to be looking at drawing fields. So, how do you draw an electrical field? Well, it's not very difficult, and it is very similar to drawing gravitational fields if you've done that. So the way that we draw the field is, since fields occupy all of the space, we can't draw that very usefully. Instead, we draw representative lines that give us an impression of the overall shape of a field. And we'll look at this again in a minute, but just to remind you that these are 3D fields, but we're going to draw 2D cross sections. So we're just taking a slice through that bit of space. If you have a point source, and our little circles here represent infinitesimal point sources, but also actually work as slightly larger sources as well. If you had a sphere with a charge on it, then you will have a radial field. So here we have a positively charged object in the center of our field, which is creating the field. The lines represent what will happen if we take a small positive charge and place it at a point in a field. The small positive charge will follow the path of the lines. Since our central charge is positive and our small test charge is positive, they will repel each other. They will repel in a straight line. So the diagram that we draw is a bunch of straight lines radiating outwards, and they have arrows, and the arrows represent the direction of movement of the small positive test charge, and they're moving away. When we say small, we mean that it is sort of physically small, it's got a small charge, therefore we don't have to worry about the motion of a large charge. Okay, even though conservation of momentum is a thing, etc., all that we need to worry about effectively is what's going to happen to the small charge. Now, again, a bit of a preview for later. We're going to be looking at the strength of an electrical field. In other words, how much force it exerts on a charge. And there's a connection here in that the strength of an electrical field is given by the density of the lines. So you can see that the lines are closer together, nearer to the central object, and further apart, further away. So that makes sense. If we take two charges, then we have a more complicated pattern. Here we have a negative and a positive test charge. Again, the negative and the positive overall charges, and again the green lines indicate what will happen to a small positive test charge. As a small positive test charge, it's always going to be arrows pointing away from the positive and arrows pointing towards the negative, because our small positive test charge will be attracted to the negative. If we put our small positive test charge midway between, it will be repelled by the plus and attracted to the minus. It will travel in this direction. We get this overall pattern. If, on the other hand, we have two charges of the same charge, then we'll have this kind of pattern. It doesn't matter if it's a negative or positive charges, if they're the same, they'll have the same overall pattern. All that's different will be the direction of the arrows. Since these are positive charges, our small positive test charge will be pushed away from both of them. So let's take one case of putting our small positive test charge here. It's pushed away from the closest one. It's also being pushed away from the furthest one, but since they are equal, the closest one has the more powerful effect. But as it's pushed away, it gets further away from the right-hand charge, closer to the left-hand charge. So the left-hand charge has more of an effect over time, and it curls away here. What would happen if we put a small positive test charge in the middle? Well, it would be equally repelled from each, and it would stay in the middle. However, that would be a very unstable equilibrium. It would only need to be fractionally closer to one or the other, and it would be pushed away. It'd be a bit like trying to balance a pencil on its point. Theoretically possible, but in reality it's never actually going to happen. Those were for point charges. What about if we have plates? So what we have here is can be a bit difficult to picture maybe, but we're looking end on at two plates. So these extend into the screen and out of the screen. One has positive charge, one has negative charge. And again, all we're indicating is what will happen to a small positive test charge. So if you put it anywhere between the two plates, it will be repelled from the positive and attracted to the negative. Hence the lines are in that direction. Other things to note, what if it was placed just outside? Well, it would have what we call the end effect. It would be bulging away. So if we put a small positive test charge here on the right-hand side, it would be pushed away from the positive, travels further, but it's now traveling close to the negative, so the negative would capture it and bring it back in. The end effects here on either side have that overall effect. Notice that the density of the electric field between the plates, not including the ends, is uniform because the lines are equally spaced. So the density between two parallel plates, it doesn't matter where you put your electric positive charge, it will always experience the same force. There is a very good interactive simulation which I will link to just to demonstrate it over here. We can drag in positive charge, we can drag in a negative charge. Notice it isn't drawing the lines, it's just doing it as a series of arrows, but you could sort of connect up the arrows to give you an indication of the lines. And here we have non-identical charges, so you can see being repelled from the positive, attracted to the negative. Or if we put two identical charges in, let's put two negatives in, then it will be attracted to, and then we have this point of unstable equilibrium in the middle where it would be attracted to both of them. I can line them up a little bit better if I put them on a grid like this. So it'll be if you put the positive charge here, it would be attracted sort of equally by both, so it would be coming here, and then at some point it would go, oh my lord, I have to turn left or right based on which one it's slightly closer to. Okay, oh yeah, and this is just one image I found, copyrights given there, to show that this is actually a 3D representation. This is something that's happening in 3D space, and all that we're able to do is take cross sections through it when we're looking at a 2D version of that diagram. So that's a quick look at drawing field lines, what they mean, how you can draw them. I hope that's been very useful. Thank you very much.